In this session, let us try to understand AC transients with RC circuit. Okay, the situation here is, though they claim maybe leading faculties or best faculties, or I don't know how to call them, but most of them are doing mistake here. Most of them means, if you have already attended coaching, just open the book of network theory, just network theory, without common sense, okay, without basics, people are extending their stupidity and they are doing such a kind of mistakes. First, let me derive something. Okay, so just to continue with me, and then at one point, okay, if you meanwhile before that only if you can identify the mistake, it's awesome. Okay, but at least let us see. Okay, yeah, AC transients RC. So already we discussed about AC transients for RC RL network. Okay, so this is RC network and this is V. Okay, for example, V equal to V max sin omega t. Okay, let me close the switch at t such that transient free condition should be there. Okay, just let me deal this way, and at one point I will stop and ask your basics. Okay, then you will understand. Okay, so means basically some current would flow I. Okay, so this particular current I will have forced response and will have natural response also, and that natural response equation will be some constant into e to the power of minus t by tau. Fine. Now what about forced response compared to voltage? Forced response in the sense at t tend into infinite, at t tend into infinite, at t tend into infinite, transients would be died out. So by that time, how much will be the current? That is the current. Okay, already we know, if I think of this as R, if I think of this as C, what is XC for steady state condition? Because this is AC, steady state condition, forced response at t tend to plus infinite. So C can be represented as XC equal to 1 by 2 pi FC, or minus J can be added. Okay, so you know how to calculate impedance here. Z mod Z equal to R square plus XC square under root. Okay, now my current, steady state current should lead, okay, steady state current under steady state conditions at t tend to plus infinite, once transient died out. Okay, so this particular current should lead voltage by tan inverse of X by R, right? So theta, if I think of tan inverse of X by R, XE by R, my current should lead. Okay, so see here. Okay, hope you will understand the mistake. Okay, now see here, if I think of voltage, source voltage, what is the source voltage? V max sin omega t. So V max sin omega t. Now if I think of forced current, okay, so if I think of forced current, my forced current should lead voltage by tan inverse of X by R, because it is capacitor dominated circuit. So my forced current should lead, maybe it will lead by angle. So this is theta, okay, like how we discussed RL network, in the same way people are trying to discuss this way. So for example, if I start from t equal to 0, if I start from t equal to 0, I cannot say minus theta, because at t less than 0 we cannot. So after this point, where I am going to get the forced response of 0, so at that instant, if I close the switch, okay, at this instant, if I close the switch, at this instant of voltage, okay, so at voltage is the reality, forced response is the mathematical, already we know. So voltage, at this instant of voltage is varying like this. Already we know that in DC voltage, DC is going to be constant like this. So wherever I close the switch, transient response, natural response, or transient response or natural response, or steady state response or forced response, or particular integral complementary function, whatever it may be. So DC is constant voltage, excitation is going to be constant. Wherever you close the switch, response will be same. But if you think of AC like this, okay, so AC, if voltage is like this, At any instant of time I can close the switch. Maybe at voltage maximum I can close the switch, or voltage 0 I can close the switch, or voltage of some negative I can close the switch, or negative max I can close the switch. So anywhere I can close the switch. For example, if I close the switch here, if I close the switch here, so what is the current actually here? What is the current actually here? So I of t is going to be forced response plus natural response. Okay, so before closing the switch, how much was the current? 0. Okay, so immediately after closing the switch, current will be 0. So under that condition, I of t for t equal to 0 is going to be 0. Okay, so under that condition, force plus natural should be 0. Force plus natural should be 0 at t equal to 0 plus. At t equal to 0 plus, force plus natural is going to be 0. So with that, if I try to apply natural equal to minus of force at t equal to 0 plus. At t equal to 0 plus. So means if force is 0, automatically natural will become 0. Getting my point, right? So I of t equal to relax, slowly, focus. Means we should stand on the basics. Okay, so total current equal to forced current plus natural current. Now total current at t equal to 0 plus will be 0. Okay, so forced plus natural at t equal to 0 plus is going to be 0. So at t equal to 0 plus, natural equal to minus of forced. Okay, as we discussed what do you say in our previous RL network also. For example, if I close the switch here, okay, so if I close the switch here, forced is having this much value, steady state current is having this much value, so forced plus natural should be 0. So natural should be of same value such that my natural response, first order or second order? First order. So natural response will decay exponentially. If I close the switch here, the blue is forced response, black is voltage source. Okay, now if I close the switch here, for example, if I close the switch here, see here, if I close the switch here, how much is forced response? 0. So how much will be natural response? 0. Okay, so basically before closing the switch, current is 0. So immediately after closing the switch, current will be 0. So immediately after closing the switch, current will be 0. Forced plus natural will be 0. So if I close the switch here, let me erase this, that may be better. Yes. Okay, so if I can close the switch here, how much is forced? Forced is 0. Okay, so at this instant, if I close my switch, forced is 0. Forced plus natural should be 0. Because at t less than 0, current is 0. Immediately 0 plus current will be 0. So forced plus natural should be 0 is the condition. So forced is 0, so natural should be 0. So our great guys, okay, I don't want to call them as faculties at all. Okay, so basically we should have minimum common sense at least. Okay, so for example, at transient free condition, okay, so this is omega t, already we know, right? In RL circuit we have seen. So if it is omega t, at what instant I have to close my switch? From here to here time. Okay, so omega t equal to this time at t equal to, at omega t equal to 0, sinusoid. Okay, V max sin omega t, that is the equation we considered. So from here to here, pi. Okay, so from here to here, pi minus theta, because with respect to voltage, current is leading by theta. So omega t equal to pi minus theta. Everything should be in radians. So t equal to pi minus theta by omega. Is it right? No. Basically, see here, kind of, it's actually very painful. Okay, so you can open your networks notes and you can think. Basically, before t less than 0, how much is the current? 0. So immediately after closing the switch, how much will be the current? Will it be 0? In inductance, current will be 0, not through capacitance. In capacitance, current can change instantaneously, but voltage cannot change instantaneously. Okay, so with respect to voltage, I can think of means 0 minus to 0 plus. 0 minus to 0 plus with respect to voltage across capacitance instantaneously cannot be changed. But here in capacitance, current can be changed. So under that condition, how can I apply? I of t equal to force plus natural is fine. But at t equal to 0 plus, how can I write 0? Okay, how can I write force plus natural equal to 0 or natural equal to minus of force such that here at this point transient free condition will come? It is actually trash. Because for example, see here, okay, for example, let me think of blue, red, okay, red only, let me continue. Okay, so for example, if I close my switch here, if I close my switch here, some voltage is there, no, at this instant, because voltage black, some voltage is there, no. Now come back to here. Oh, sorry. Yes, come back to here. So before closing the switch, let us consider that my capacitance is, so means kind of relaxed, initially relaxed, such that voltage across capacitance at 0 conditions is 0, initially relaxed, no energy storage. Let us consider initially relaxed. Now, if I close the switch at that particular instant, so immediately after closing the switch, what will happen? This much amount of voltage will be appeared here. Okay, so see here, this much black, think of black. So from here to here, that much voltage will come here instantaneously. Okay, how much is the instantaneous voltage here? Voltage cannot be changed. So 0 minus voltage is 0. So 0 plus voltage should be 0. So short circuit. So the moment you close the switch, instantaneously this much voltage divided by resistance, that much amount of current will flow. Getting my point, right? So if I have that much voltage black, see here, so this much voltage if I maintain at that particular instant of closing the switch. Okay, so if we think of switch here, switch is closed at that particular instant, that much particular voltage, instantaneous voltage is there. Okay, so initially relaxed capacitor, if I think, okay, so initially relaxed capacitor means at t tending to 0 minus means voltage across this is 0. So immediately after 0 plus, voltage across that will be 0. Okay, so instantaneous voltage is there and resistance is there. At that instant, this particular voltage, this particular voltage divided by that resistance, because this is short circuit, because initially it is relaxed. So huge currents will flow or not? Yes. So now can I say this as a transient free condition? Can I say this as a transient free condition? How bullshit it is. Okay, anyway, let me think of in what way we have to deal. Basically, we understood duality. Okay, so let me go ahead with duality. Let us think of resistance, parallel capacitance, and with current source. Okay, so this is I u of t. In the sense that t equal to 0, rather than connecting the switch directly, I connected that way. So I into u of t. What is that I? I equal to I max sin omega t. Okay, so if I try to draw waveform of I, okay, I max sin omega t, okay. Now if I think of voltage across this, okay, so at t less than 0, how much is the voltage? At t less than 0, this is going to be short, or I can think of there is no voltage across this. Means at t less than 0, even if it is open circuited, because current source, even if it is open circuited, means whatever the energy stored here, that energy might have dissipated in this resistance. Okay, now at t equal to 0 plus, how much is the voltage? 0. Okay, now I can apply 0 minus to 0 plus properly. Now anyway, coming to the point, see here, if I think of v of t equal to forced plus natural, okay, natural is going to have exponential decaying function because that is first order. Okay, now let us think of forced. Okay, so forced function in the sense that t tend to plus infinite. At t tend to plus infinite, it is going to be steady state condition sinusoid. Okay, so if I think of my vf, forced response, my current should lead, or with respect to current my voltage should lag. So let me consider like this. Okay, now if I think of closing the switch, because this is forced response. Okay, for example, if I close the switch here, okay, see, at t equal to 0 plus, at t equal to 0 minus, how much was the voltage across capacitance? 0. So at t equal to 0 plus, voltage will be 0 only. So v equal to forced plus natural. Total response is going to be 0, is going to be forced plus natural, or I can say that natural response is going to minus of forced. at that instant. From that and onwards, exponential decaying function will be there. So if I connect here, okay, so this is going to be forced response. Now same amount of natural response should be there. Natural response will decay slowly, exponentially. Getting my point, right? Now for example, if I try to close my switch here, okay, so how much is the forced response? Red, forced response red. So forced plus natural should be 0. Forced plus natural should be 0 because at t less than 0, voltage across capacitance is 0. So at t equal to 0 plus, voltage should be 0. So forced is already having some positive value. Forced plus natural should be 0 at t equal to 0 plus. So natural should be minus of force. So force is having this much. So natural will decay like this exponentially. How to find time constant and all we know. Okay, now if I close my switch, here, maybe let me erase this. Yes, so if I close my switch here, then what will happen? What is forced voltage is 0. Okay, so at t equal to 0 plus, forced plus natural should be 0. At t equal to 0 plus, because at t less than 0, voltage is 0. So at t equal to 0 plus, voltage cannot be changed from 0 minus to 0 plus across capacitor. So voltage is 0. So forced plus natural should be 0. Because total response is forced plus natural. So natural response is equal to minus of forced. Forced response is 0 here. If I close my switch here, forced response is 0. So automatically natural response will become 0. So in order to have transient free response, this theta has to be considered. Okay, so in order to have transient free response, if I think of omega t here, okay, so in order to have transient free response, okay, so omega t equal to theta or t equal to theta by omega. Okay, if they have any shifting property for the current, under that condition sin omega t plus pi will come, like what the way we discussed in RL network, in the same thing will be proceeded here. Okay, so for example, if they give you Imax cos omega t, so we are going to take the reference. Okay, so we are going to take the reference from here, cos omega t. So after that, when you are going to have forced of 0 here, okay, because if I think of cos omega t, see here, I cos omega t, black cos omega t, I am going to start from here. After this, when you are going to have 0 crossing of forced voltage across capacitance, okay, is here. So in order to have transient free, we need not remember formulas, equations and all, not required. Okay, so see here, from here to here theta, see, from here to here leading by theta, and from here to here pi by 2. So in order to have transient free, okay, so omega t equal to pi by 2 plus theta, or t equal to theta plus pi by 2 by omega. That's it. Okay, so we need not remember any formulas or equations, we need not have any tables here. Okay, just maybe if they give cos omega t, it will be shifted. After that, where you are going to get, see, from black to black maximum to black 0 pi by 2, and from black 0 to red 0 theta. So in that way we can calculate. Okay, now what will happen for previous circuit of this then? This. Okay, for this RC circuit, RC in series, how to find transient free condition? Will there be transient free condition or not? Yes, because AC transient free condition will be there. And how to calculate time, at what point we have to close the switch in order to have transient free? Laplace transform will give you the information. Okay, just like that, like see, we have seen previously. Okay, so RL network, if you compare RL network here, Okay, with RL network, what happened? Before closing the switch, inductance current is 0. So immediately after closing the switch, inductance current should be 0, such that forced plus natural should be 0. So for this, I can use just like okay, convert this into as usual. Actually, people are what they are doing is they are keeping voltage here, they are keeping resistance here, they are just removing inductance and they are replacing with capacitance, and they are saying this, and somehow without all this, somehow they are what do you say? You got my point. Okay, no, for this circuit, transient free condition directly we cannot find. Okay, for this circuit directly we can find, or if I have only RL in series with voltage source also we can find. Okay, yeah.